Hi. In the previous video, we discussed the classical application of backtracking, the N-Queen's problem. In this video, we are going to discuss yet another application of backtracking, the sum of subsets problem. What is the objective of this particular problem? The objective is to find subset of elements that are selected from a given set and whose sum adds up to a given number k or a given sum s. The assumption that we have here in sum of subset problem is the input set should be unique. That is, there should be no repetitions in the input set, one. The second assumption that we have here is the numbers should be non-negative. And the third assumption that some of them take while calculating this, while performing the sum of subset problem is the list of elements should be in sorted order. But here we consider that the input set should be unique and there should be no negative elements. The approach that we follow for solving the sum of set problem is brute force approach, backtracking. And any backtracking problem will be having something what we call as a constraint. A constraint, as discussed, as we said earlier, is a restriction, okay, that helps us in getting the solution. And the output of any backtracking problem will be a number of solutions that satisfy the constraints. In this case, all possible subsets that satisfies the constraint will be the output. Let us take an example. If W is the set and sum is as given as 15, then the subsets are 8, 7, 7, 5, 3, 6, 9, and 5, 10. All these four subsets adds up to the sum 15. Okay. So now we are going to discuss about two different backtracking approaches. One backtracking approach is with constraints and the other backtracking approach is without constraints. So at the end, we will compare both these approaches and see which one is more effective. Right. Let us take at the first method, backtracking approach with constraints. So given is nothing but a set of weights 5, 10, 12, 13, 15, and 18. That is, the number of elements in the set is n is equal to 6. The objective is to obtain subsets such that their sum is exactly equal to s. In this case, s has been given as 30. So our solution should have a subset of elements that sums up to 30, exactly 30. How will the solution be represented basically? Here we are going to represent the solution in the form of 0, 1 format. Okay. Suppose M is an array which can hold values from 1 to 6, right? Mi is equal to 1, then the weight is part of the subset. When Mi is equal to 0, then the weight is not part of the subset at all, right? Suppose, okay, 1, 1, 0, 0, 0, 0 means that the first element and the second element are part of the subset, whereas 3, 4, 5, and 6 are not a part of the subset. Right. So any backtracking problem is something which will definitely have a constraint, right? So here also we have two constraints in this sum of subsets problem. Okay, the constraints are given as bounding function 1 and bounding function 2. Normally we call a constraint as a bounding function in a backtracking problem. Earlier in N-Queen's problem also we had some bounding constraints, bounding functions, right? So before getting into the equations of these bounding functions or before getting into the definition of the bounding function, let us take an example, try solving it, and then explain what the bounding function is. For the time being, just remember that there are two bounding functions, bounding function 1 and bounding function 2. Okay. The solution of the sum of subset problem is represented in the form of a state space tree. Okay. So state space tree, we are going to generate the state space tree for one solution. As denoted earlier, W denotes the set which contains 6 elements. All right. So where do we start? Okay, B1 and B2 are bounding functions as we discussed earlier, but I haven't told you what B1 and B2 is. Let us go to B1 and B2 later. Let us start constructing the state space tree. The initial state here will be 0, 73. What does 0 denote and what does 73 denote? 0 denotes that As of now, there are no elements as part of the subset. And 73 denotes the total sum of the elements of the subset. That is 5 plus 10 plus 12 plus 13 plus 15 plus 18. The sum of all the 6 elements comes to 73. So why do we need this? What is the point of needing this? We'll see that later, right? So now what we are going to do is, we are going to perform a depth first search. Backtracking follows depth first search, whereas branch and bound follows breadth first search. We know that, we have discussed that earlier. In the first video, in the introduction to backtracking, we have discussed that, right? So what we are going to do is, we are going to include element 5, that is the first element, as part of the subset. So when you include element 5 as part of the subset, okay, we are subtracting 5 from the total, 5 comma 68. Okay, so this total is needed for the bounding function. In what way? We will again see that, right? So now the first element 5 has been included as part of the subset. Then we are going to include 10 as part of the subset, so that 5 plus 10 becomes 15. The sum of the element is stored in the first level, 15, and 10 has been subtracted from 68. So the value becomes 15 comma 58. Next, we are going to include 12 as part of the subset. So when you include 12 as a part of the subset, the sum becomes as 27, right? What is the bounding condition that we have? What is the constraint that we have? S should be 30, right? Your sum should be equal to 30. The sum of the subset should be equal to 30. That is the constraint we had earlier, right? What we have here is 27, right? Let us proceed further, right? Let us include the next value of the set into the subset, that is 13. When you include 13 as part of the subset, the sum now becomes 40. But what is the constraint we had? The constraint is that the sum should be equal to 30, exactly equal to 30. So here bounding condition 1 occurs. Bounding condition 1 occurs. So now we will define what bounding condition 1 is. Bounding condition 1 is nothing but, let us go back to the definition of the bounding condition and see. The sum of the weights included so far plus the weight of the next object should be less than or equal to S. The sum of the weights included so far plus the weight of the next object should be less than or equal to S, right? So here, how the sum is calculated? Initially sum is 0, then sum becomes 5, then sum becomes 15, then sum becomes 27, and then sum becomes 40. The sum of the elements included so far, 5 plus 15, 5 plus 10 plus 12, which amounts to 27, right? Plus the weight of the next item, which is 13, should be less than or equal to 30. But the value here is greater than 30. That is bounding condition 1. So what we have to do here is, we have to stop the solution with here and we have to backtrack it. So what we are going to do, we are going to backtrack by omitting the 13th element as part of the subset. So without 13, what will be the value? 27 comma 33. That is, we are also subtracting 13 from the total 46. So now what we have is 27 comma 33. So we have included 5, we have included 10, we have included 12, and we have excluded 13 as part of the subset, right? So 5, 10, 12 and 13 are included, 13 is excluded. Next we shall try by including 15 and see whether the sum becomes 30, right? So with 15, again what happens? The value becomes 42. So this is again bounding condition 1. The sum of the elements included so far plus the weight of the next element should be less than or equal to 30. Here it becomes 42, right? 5 plus 10 plus 12 plus 15 becomes 42. Again bounding condition comes 1 or occurs, B1. Backtrack and try without 15. That is, we have included 5, 10 and 12. Now we are excluding 13 and 15, right? So when you exclude 15, the value, the sum will be 27. Okay, and 15 will be subtracted from 33, which is 18. Now, what is one more element left? The last element is left. So, include 18 as part of the subset. When you include 18, again what happens? The sum becomes 45, which is again bounding condition 1, because it should be less than or equal to 30, right? So, again backtrack and try without 18. When you try without 18, the value will be 27, 0, right? This is bounding condition 2. So, what is bounding condition 2? The sum of the weights included so far, the sum of the elements included so far, plus the next weight should be greater than S. Okay, let us go for the definition and see. Sum of the weights included so far and the remaining weights should be greater than S, that is B2, right? Because what the sum we need here is 30, but what we have here is 27, and the next weight is 0, right? So 27 plus 0 is always less than 30. It can never be greater than 30. So this is bounding condition 2. Now we have exploited all options with by including 12 as part of the subset. That is, we have included 5 first, we have included 10 first, we have included 12 next. So what we have here is 5 plus 10 plus 12, 27, right? But when we have 27 and proceed further by including 13, 15 and 18, we don't get the solution at all. Okay, so let us proceed by excluding 12. So without 12, how do you proceed? That is, we have 5 and 10 as part of the subset. We exclude 12, and what we get here is 15, 46. 5 plus 10, 15, and we are excluding 12. So 58 minus 12 is 46. So 5 we are part of the subset, 10 is part of the subset. Next we are excluding 12. So let us try by adding 13 as part of the subset. When you add 13 as part of the subset, okay, the sum becomes 28 and the total becomes 33. Yes, it becomes 33, right? Okay, 28 is less than 30. We can still proceed. Let us include 15 as part of the subset. When we include 15 as part of the subset, sum becomes 43. So what is the bounding condition here? B1. Let us backtrack and try without 15. When you try without 15, we have 28, 18. That is, we have excluded 15. So you need to subtract 15 from 33, 18. 28, it comes as it is. Okay, now we have one more element, 18 left. Try including 18 as part of the sum. The value becomes 46, 0, which is bounding condition 1. Backtrack and try without 18, the value becomes 28, 0, which is bounding condition 2. Okay. Now we have exploited all options by including 12 and by excluding 12 also, right? Okay, now we need to backtrack still. Okay, now what we have is we have 5 and 10 as part of the subset. So we are backtracking here. Okay, so before backtracking there, we go for one more option. That is, with 13 we have included. Next we are trying for without 13. When you try for without 13, we have 15, 33, right? Okay, when you proceed, once again what we have is we include 15 as part of the subset. So now we get the sum as 30. Now we get the sum as 30. So which is the solution which we need so far? 5 plus 10 minus 12 minus 13 plus 15. That is, we are including 5 and 10. We are excluding 12 and 13, and we are including 15 as part of the subset. So 5 plus 10 plus 15 is 30. So this is the solution that we have got. Okay, so we have satisfied the constraint, sum is equal to 30. Okay, now the output will be in the form of 1, 1, 0, 0, 1, 0, where 1 denotes that the element is part of the subset and 0 denotes that the element is not part of the subset. So 1 refers to 5, the next one refers to 10, okay, 0 refers to 12, 0 refers to 13, and 1 refers to 15. So 5 plus 10 plus 15 is 30. So this forms solution 1. And if we still backtrack and go further, we will be having further solutions for this sum of subsets problem. So let us look at the possible solutions with constraints. One possible solution is we have found out 5, 10, 15. Another possible solution is 5, 12, and 13. Okay, and the last possible solution is 12, 18. So for this sum of subset problem with constraint, there are three possible solutions. Okay, when n is equal to 6, not when n is equal to 6, for the given n is equal to 6, right? Okay, so this is one part of sum of subset problem. We have discussed the sum of subset problem by including constraints, right? Okay, what happens when the sum of subset problem is done without constraints? So when there is no constraint at all, the disadvantage here is the number of solutions will be more. That is, the given weight, the same number of weight are given. Objective is to obtain subsets of the given weights. No constraints are given. And the problem here is, okay, the number of solutions will be 2 power n. That is 2 power 6. There will be 64 solutions for a backtracking approach without constraints. Whereas for a backtracking approach with constraints, there are just 3 solutions. Right? So let us see a partial state space tree without constraints. We have already drawn the state space tree with constraint. We have found out one solution, but I am going to just draw a partial state space tree without constraint. You can see, okay, how many solutions are there. Since it is a depth first approach, we always go this way. I am just pushing the animation forward. You know how this works. So the first solution will be, okay, we will be including 5, 10, 12, 13, 15 and 18 all as part of subset. This is solution number 1. The second solution will be, a subset will be 5, 10, 12, 13, 15 and 18. Okay, similarly, you will be going for all possible solution. You will just backtrack and find out all possible solution. This animation lets you just go through, okay, how a sum of subset problem, how a state space tree will be constructed for a sum of subset problem without constraint. Okay. Due to space availability, I have just drawn up to a certain level, right? So this particular state space tree without constraint, the complete state space tree without constraint will have 64 solutions, that is 2 power n solutions. So which is more efficient? The sum of subset problem with constraints is always more efficient. All right. So let us just go for the steps that are available in the sum of subset problem. Then we'll see a simple algorithm of the sum of subset problem, and then finally we'll see the applications of it. All right. Let W be the set of elements and S is the expected sum of subset. So where do we start the sum of subset problem? Always start with an empty set. That is, we always start our state space tree with 0, right? The subset is empty initially. The set is full, the subset is empty, 0. Add to the subset the next element from the list. So from the set, okay, add to the subset the first element from the list or the next element from the list. If the subset is having some S, then stop with that subset as solution. Okay, if when you are adding the first element as part of the list and it is equal to S, for example, first element is 30 and the sum is 30, right? When you add 30 to the list, okay, the sum and what? The subset becomes equal, right? Then you have to stop there. If not, okay, if the subset is not feasible, or if you have reached the end of the set, then backtrack through until you find the most suitable value. Okay. Then fifth step, if the subset is feasible, repeat step 2. And last step, if all the elements are visited without finding a suitable substep and no backtracking is possible, then stop without solution. These are the 6 steps, okay, for a sum of subset problem. Start with an empty subset, okay, add element one by one and see whether it is equal to the sum S. If it is not equal to the sum S, or if it exceeds sum S, stop it, okay, backtrack and try finding out, okay, where you will get the sum S. If there are no solutions at all obtained and no backtracking is also not available, then stop without solution. So these steps sum up how to work, how to generate the state space tree for a sum of subset problem, or how to solve the sum of subset problem using backtracking. And this is the algorithm. Okay, this is the algorithm. So this what we call as procedure has the following parameter. Set is nothing but the given set, that is the number of weights that we have. Subset is the set which we are going to construct. N is the size of the set, given set. For in our example, N is equal to 6, and subset is the size of the subset. Subsize is the size of the subset. Okay, total is nothing but the total of the subset. Okay, and node is number of elements in the subset, and finally, okay, sum is the given sum. If total is equal to sum, then you need to display the subset, and then try finding out the next solution. Else you need to backtrack and find out the solution here. Okay, we have seen in detail about this algorithm. This algorithm is nothing but a a recap of how the actual sum of subset problem works, right? And finally, we are going to see about, okay, the application of sum of subsets. The subset sum problem could be used to solve many other problems. Basically, these problems can be used to solve by using sum of subset problem, factoring, traveling salesman, any integer programming problem, satisfiability problem. It can also be used to generate computer passwords and message verification. In the next video, we are going to take a look at the Hamiltonian circuit. Thank you.